Swayam Prabha. Digital India. Educated India.
Welcome to the third lecture on energy based techniques. So far we just looked into the basic of the energy principles and we applied it to one simple structural problem. Now we will see how we can apply this technique to problems where piezoelectric patches are fitted in a structure. So again we have come to our this known structure where I have a beam with piezoelectric patches. So for this beam, if I want to write down the virtual work form, it looks like this: sigma multiplied by delta epsilon minus dz multiplied by variation of the electric field minus. So let us assume that it has forces distributed along x, some external forces, external load, and that we call Px, and then there are distributed forces along z direction also. The distribution can be anything, they need not be uniform, and that let us call that Pz. So we have here Px multiplied by variation of u0 dx, and that goes from 0 to L Pz variation of w dx minus surface integral of charge multiplied by variation of the potential delta V, and that is over the surface. So to understand this, in this problem we have the piezoelectric patches and they can be actuated with voltage, and there can be external loads which are shown as Px and Pz. And as we have seen that depending on the forces and depending on the type of actuation, there can be extension as well as vertical displacement. So u0 is pure axial displacement, so axial displacement at the mid of the beam, and w is vertical displacement. And we know that u at any x and z is u0 minus z into del w by del x, and here u is 0 is function of only x and w is a function of only x. So here we are using again the Euler-Bernoulli based formulation we will do. Euler-Bernoulli assumption we will take and we will formulate it accordingly. So in this case the unknown stresses and strains are only f sigma xx and sigma and epsilon xx. So because that is the only unknown I mean the only non-zero component, unknown as well as non-zero, we do not consider other stress or strain components, those are the only existing components. So I did not put any subscript, so just sigma and epsilon. So there this is sigma xx and this is epsilon xx. And in the piezos there is electric field is in the third direction, the z direction. So, E3 that is Ez because z is 3 direction, and similarly dz is equal to d3. So, we can see that apart from these components which come from the mechanical quantities, we have components which come from the electrical quantities as well. So, if I just only consider this and this, that is quite familiar to us. We have the internal virtual work and these two gives us the external virtual work, but we have introduced now these two quantities that come from the mechanical electrical part of it, and we will see how it came to it, why this is negative and so on. So, let us spend some time on deriving this. So, this is our virtual work equation. Now, before directly using it for our other formulations, I mean, let us spend some time on deriving this. So, we will derive it for a generic 3D case, and then whatever we did can be a specific case of it. So, we can write sigma ij comma I multiplied by variation of uj dV integral over the volume plus dII multiplied by the variation of the potential V equal to 0 as our equation to start with. Now, how from where did this equation come? Sigma ij comma I is just the conservation of linear momentum. So, sigma ij comma I equal to 0 is just the conservation of linear momentum. So, from the conservation of linear momentum that we saw before, we have sigma ij comma I plus bj any body force, and that is equal to rho uj double dot. Now, here bj is the body force. If we assume that there is no body force, and we have anyway assumed that there is no body force due to the interaction between the polarization and electric field, and apart from that there is no other body force also. So, it is not there, and it is a static problem. So, uj double dot is also 0. So, we are left with only sigma ij is equal to 0 after we set them equal to 0, and d I comma I equal to 0 comes from the Gauss law. So, the first equation, which is the conservation of linear momentum, sigma ij comma I equal to 0, if I multiply that with the variation of displacement, and d I comma I if I multiplied with the variation of the potential, and then add this, we get this, and then we set it equal to 0. Now, this expression can be rewritten as sigma ij del variation of uj comma I dV minus sigma ij variation of uij comma I dV. Similarly, this can also be rewritten as product of di into variation of potential phi comma I minus di into variation of potential comma I, and then again dV equal to 0. Now, how could we write this? So, if I just look at this expression sigma ij del uj comma I. So, that is differentiation of this entire quantity inside the bracket with respect to xi. So, it can be x y z depending on what is I goes from x y z, I goes along x y z. So, if I differentiate it, we first differentiate this, keep this as same, and then we keep this as same and differentiate the second quantity. So, it becomes del ij comma I, sorry, sigma ij comma I into variation of uj plus sigma ij multiplied by variation of uj comma I. So, this we had. So, this equal to this quantity minus this quantity that we have written here. In the similar way, we can write this also as this. Now, if we apply the Gauss divergence theorem here, it becomes a surface integral, and we have sigma ij ni. Ni is the unit normal at the surface along direction I, then ds, and then we have sigma ij. So, uj comma I is epsilon ji, and but we know that the stress tensor is symmetric. So, that we can write as epsilon ij also. So, this becomes epsilon ij, and then we have di ni, then variation of the potential phi. So, it is a surface integral and here we have di. Now, phi comma I is nothing but negative of the electric field, because we have seen that electric field as a vector is minus of the gradient of the potential phi. So, and which is equal to minus, from here we can just write that E electric field along I direction is just minus of phi comma I. So, this quantity gives me d I multiplied by the electric field along I direction dV. So, this is how we derive it. Now, this is variation of the potential, and we know that the voltage is just potential difference. So, with all these, this is the expression in the 3-dimensional system. So, for our system we can reduce this equation to this form, and that explains why this quantity is negative, where from these quantities came, and so on. Now, just to explain one more thing, d I n I is the charge. Now, in our problem, when we have actuation, we are actuating by these quantities, these piezoelectric patches by voltage, then the voltage here and the electric field here are known to us, which means the variation of potential and the variation of the electric field are 0. So, we can discard this quantity and this quantity when we formulate it for the actuation problem. So, we will have only this and this would suffice for us. And also if sometimes the charge can be taken to be 0, in that case also this quantity is discarded. So, depending on the problem that we are solving, we can keep some of the quantities, we can discard some of the quantities. And here this expression is written just in general. If you want to write it for the two piezos separately, then we have to write for this surface and this surface separately for these two piezos. So, as we said, now we will discard these two quantities because we know the variation of potential and the electric field, and then we will move on. So, now let us write it once again. So, now we will write the governing the virtual work equation, and then from there we will find out the from the virtual work equation we will find out the equilibrium equation that we are using last week. So, the virtual work equation is sigma multiplied by variation of strain. So, here we have only one stress component, that is sigma xx, and one strain component, that is epsilon xx. So, we are not using any subscript, and then we have this as the external virtual work component. And that is equal to 0. Now, we know that epsilon is epsilon 0 minus z kappa, and sigma is E multiplied by epsilon 0 minus z kappa minus epsilon p. So, if we put it here, we get E multiplied by epsilon 0 minus z kappa minus epsilon p minus epsilon 0 multiplies by z kappa and volume integral, and then we have again p x, this remains as it is, and that is equal to 0. Now, what we do here is we separate out whatever is multiplied with delta epsilon 0 and whatever is multiplied with delta kappa. So, if we do that, we have epsilon 0 minus z kappa minus epsilon p minus multiplied by delta into epsilon 0, and then we have z into E, we just take this z out, and epsilon 0 multiplied by z kappa multiplied by epsilon p, and that multiplied by delta kappa. And then we can break down this volume integral into a cross sectional integral and a integral over the line 0 to L. So, this is our area over the cross section A, and this goes from 0 to L. Now, while treating this, we will do integration by parts here. So, let us take this first. So, we have delta of u 0 multiplied by integral of p x dx, and the entire thing evaluated at x equal to 0 and L, plus we have differentiation of this. So, if I differentiate u 0 with respect to x, that gives me epsilon 0. So, we have delta of epsilon 0 multiplied by p x dx 0 to L, and again we have to take care of this. So, we do the same thing, delta w p z dx evaluated at 0 and L, and then plus. So, after this whatever the term is, I am writing it here for a reason, plus we get delta of del w by del x into p z dx integrated over 0 to L. But this can again be further separated. So, if we do that, we get plus delta of del w by del x multiplied by p z dx dx, and this entire thing evaluated at 0 to L, and then minus integration 0 to L, and then if I differentiate once more I get del 2 w by del x 2, which is nothing but kappa. So, delta kappa multiplied by the p z integrated twice, and then this entire thing integrated over 0 to L, and that is equal to 0. Now, if we look here, E epsilon 0 when integrated over A, that gives me E A total. So, we have E A total multiplied by epsilon 0 minus Z E on being integrated gives me E S total. So, we have E S total kappa, and E epsilon p on being integrated gives me N p. So, this multiplied by delta epsilon 0 dx. Now, when we treat this, we have minus z into epsilon 0 integrated over dA. So, that will give me E S total into epsilon 0 minus z into minus z, that is plus z, and so z square E integrated over A, the area will give me the E I total. So, here I should have one more E also. So, that is E, the elastic modulus is missing here. So, it will give me E I total kappa, and then the kappa sign should not be there. So, yeah, instead of kappa E should sit over here. So, now, so that gives me E I total E z square kappa. So, E I total kappa, and then I have minus M p that we get from these two terms and epsilon p, and that multiplied by delta kappa dx. Now, if we look at these terms closely, so p x on being integrated, it gives me minus of n. So, we can quickly check it here. So, suppose if I take a section somewhere here, and then if we look at the structure from x equal to 0 to that. So, suppose it is some x and I take a section there, and then if we look at the structure from x equal to 0 to that part, and suppose there are reactions depending on the force, there can be reactions, some force, I am just showing some axial forces, whatever it is. So, please do not understand, it is just to show any force, these directions does not matter. So, if I sum up these forces, and that force is equal to negative of this force n for equilibrium. So, integration of p x gives me minus of n. So, this is minus of n, and similarly integration of p z gives me the shear force V. So, this is V, and again p z when it is integrated twice, which means when shear force is integrated once, that gives me bending moment m, and this is bending moment m. Now, if we look at this boundary term, this term is 0, because at x equal to 0 I have u specified, it is a clamped. So, delta of u 0 is 0. At x equal to L I have no axial force, at x equal to L I have no n here. So, it is 0. So, this term vanishes. So, this goes to 0. This term again the boundary term at x equal to 0, W I know that it is specified, which is 0 for our case. So, delta W is 0, and at the tip there is no shear force. So, it is 0. Similarly, again at the clamped end the slope is specified. So, delta of this del W by del x is 0, and at x equal to L the no bending moment. So, m is 0. So, this term, these terms are all going to 0. So, I have this and this remaining. So, that gives me minus of 0 to L n del epsilon 0 dx minus 0 to L m del kappa dx equal to 0. Now, we can again rewrite this as plus this is E I Now, we know that this del epsilon 0 and delta kappa, they are independent variations. So, they can only be 0 when this is equal to 0 and this is equal to 0. So, that gives me again these two equations, E A total plus E S total minus N P minus N and E S total epsilon 0 kappa. So, we have epsilon zeros here. So, E S total epsilon 0 plus E I total kappa minus M P minus M equal to 0. So, this is the equation that we dealt with last week. So, instead of balancing the forces, we got it starting from the virtual work equation. Now, with that I would like to conclude this video here. Thank you.